So today's topic is about the materials, and in this one we'll discuss about the stress, strain, and the Young's modulus. How we define the term stress? Stress is actually the force acting on unit area. How much force we applied on a unit area, we call that as a stress. And the concept of the stress is same as the pressure. How we define the term pressure? Pressure is also force acting on unit area. But whenever we use the term pressure, pressure is always refers to whenever we apply force which is 90 degree or perpendicular to the surface. The force which is perpendicular to the surface or force acting on a unit area perpendicular to the surface, that is refers to pressure. But in case of the stress, it's not really the force should be perpendicular. Force can make certain angle. So the total force which is acting on a unit area, we call that as a stress. Stress is of different types. Once we have a tensional or a tensile stress. What is the meaning of the term tensile stress? When we apply force on a unit area to stretch an object. So we applied a force on a specific area so that the object can stretch. What we call that as a tensile stress or tensional stress. When we apply force on a unit area to reduce the size of an object, what we call this stress, we call that as a compressive stress. And we have a shear stress. What is the meaning of the term shear stress? Shear stress means we apply force on the layers so that the layers can slide over each other. So when the two layers, group of the particles slide over each other, that stress is known as the shear stress. So stress is force acting on unit area. But what is the difference between a stress and the pressure? Whenever we calculate the pressure, that the force should always be 90 degree or perpendicular to the area. But in case of the stress, when we are calculating a stress, the force can be perpendicular, may not be perpendicular. That does not make difference. So that's the main difference between the stress and the pressure. So even I can also say this as a stress, the force which is acting on unit area, this is stress or a pressure. But this one I cannot say pressure. I have to take the component of the force if I want to calculate the pressure. So if I say there's a force, like there's a cross-sectional area of a 2 meters square and it experiences a force of 10 Newton. What is the pressure here? The pressure will be 10 divided by 2. So the pressure will be 5 Pascal. If I say what is the stress? Stress is denoted by the Greek alphabet sigma. The force is 10 and the area is 2. So 10 divided by 2, I will get 5 Pascal as well. So in this case, the stress and the pressure is same. But what if the force is not exactly perpendicular? The force was making certain angle. So the force of 10 Newton was making certain angle. If I want, and say it was making an angle with a vertical 20 degrees. So if I want to, and the area is again 2 meters square. So if I want to calculate the pressure here, so the pressure, I will take the perpendicular component. So in that case, it will be 10 cosine 20 divided by 2 meters square. That will be the pressure. But when I calculate the stress, I will use 10 divided by 2. I will get that as 5 Pascal. So when we talk about the stress, we don't bother about the direction of the force. But in case of this, the pressure, the force must be perpendicular to the cross-sectional area. The unit of the pressure and the unit of the stress is same and they have the same base units. Is it clear? The concept of stress and the difference? Both stress and the pressure are scalar quantities. Even the pressure is also a scalar quantity because the vector addition rule is not applicable. That's why it is a scalar quantity. Stress and pressure both are scalar. They don't have the resultant direction. So when we want to calculate the stress, we don't take the It's like how much, for example, if I want to calculate the stress, I don't take the component of the force. If this was having an area 2 meters square, and I want to calculate, like I'm applying a force of 10 Newton. So what is the stress here? 10 divided by 2, I will get 5 Pascal. So we don't take the component. We just take the force and divide it by area. But when we need the pressure, then we always, because the definition of the pressure is the force which is perpendicular to the surface. So I'll take the perpendicular component of the, because the definition of the pressure state, the force which is perpendicular to the surface or the cross-sectional area, that is known as the pressure. So if I need the pressure, I will take the perpendicular component. But if I need the stress, I don't have to take or divide into component. And the unit of the force is Newton, and the unit of cross-sectional area is meter square. So it is Newton per meter square. The cross-sectional area changes depending on the shape. Example, if you want to take the cross-sectional area of the wire, say a wire is there, and you apply a force, say a 10 Newton force is applied, and you want to calculate the stress. So stress is force acting on unit area. So it will be force. What about the area? So we'll take the cross-sectional area of the wire. So what is the cross-sectional area of the wire? It will be the cross-sectional area, which is pi r square. That's the cross-sectional area of the wire. But we have, like example, a cube or a cuboid is there, and we want the area. So in that case, we'll take the area which experiences the force. So force divided by area. So it will be force divided by, if one side like length and width is there, so length multiplied by width, we'll get the cross-sectional area in that case. Is it clear? The definition of the stress and the difference between a stress and the pressure? Any doubt in this? Then we have a strain. How we define the term strain? Strain is actually the ratio, the comparison between the change in the length and the original length. How much the length has changed compared to the original length, we call that as a strain. Example, the wire is there which was having a length of 2 meters. It is subjected to a force, and the wire has new length of, like example, 2.3 meters. So how much the strain is refers to the change in the length compared to the original length. So what is the change in length? Originally it was 2 and now it's 2.3. So the change in the length is 0.3. And what is the original length? The original length is 2. So the ratio between the change in length and the original length, that is refers to strain. So we can say the strain will be equals to 0.15, but we don't write a unit. Why we don't write a unit? Because it's a comparison, it's a ratio, and ratio does not have any unit. Like a refractive index of a material, which is a comparison between the tendency of a material to bend light compared to that of air. So refractive index does not have any unit. Same thing, the strain is not having any unit. It's just a value, a number is there. So we say strain is 0.15. Strain can also be represented in percentage, which make it much more easy to understand. So if we need a strain in the percentage, so it's a change in length divided by original length into 100. So in this case, the change in length was 0.3, the original length was 2, and multiplied by 100. So 0.3 divided by 2 was 0.15, and when we multiply by 100, we get a percentage. So means the strain is 15%. What does it mean? The significance of a strain to be a 15%, it means if this subjected to a certain force, it will change the length 15% of the original. So in terms of percentage, it's easy to understand and express as compared to that in decimal or a fraction. So strain is a comparison between the change in length and the original length. Is it clear? The concept of strain? And what is the Young's modulus? The Young's modulus is actually showing a relation between the stress and the strain. So according to the Young's modulus, stress which we apply on the object is directly proportional to strain. Stress means force acting on unit area, and strain means the change in length divided by original length. So if I have a wire or a spring, usually we use for wires, but it can be used for the spring as well. Example, if I have a wire and I attach a load of 2 Newton and another identical original length wire, and I attach a load of like 20 Newton, so the wire which is subjected to a high stress will show a greater strain. Like if I apply more force on unit area on the wire, I will find that the wire will show a greater change in length. So according to the Young's modulus, stress is directly proportional to strain. So we can say stress is denoted by sigma and strain is denoted by epsilon. This is the symbol epsilon, not E. It's a Greek alphabet. So stress is directly proportional to strain. And whenever we remove the proportionality relation, we always replace with equal to and a constant. So when we replace this proportionality, we'll write an equal to and the constant of the proportionality, which is a Young's modulus, can be denoted by letter E into epsilon. And what about the Young's modulus? If I need the Young's modulus, so Young's modulus will be equals to stress divided by strain. So stress is directly proportional to strain. Whenever you replace the proportionality sign, like if I say X is proportional to Y, if I replace the proportionality sign, I will replace with equal to and the constant of the proportionality, which is K here. So if I need K, so it will be X over Y will be equals to K. Same thing, stress is directly proportional to strain. If we apply a greater stress, the object will show a greater change in the length compared to the original length, or it will have a greater strain. When we replace this proportionality sign, we replace with equal to and a constant for the equation. In this case, the constant of the equation is known as the Young's modulus. So Young's modulus is actually the ratio between stress and strain. And if we substitute the values, like stress is force acting on unit area, and the strain is the change in length over original length. When I simplify this equation, the Young's modulus will be equals to FL divided by delta XA. So if I know the force applied on the object, if I know the original length, cross-sectional area, and the change in length, so I can work out the Young's modulus. So Young's modulus, it's the same concept like force is directly proportional to extension, or F is equals to KE, or F over E is equals to K. Here this K is known as the spring constant or the proportionality constant. Same thing here, E is representing the Young's modulus or the proportionality constant between the stress and strain. Is it clear, the concept of stress, strain, and the Young's modulus? Any question or doubt till this point? Any doubt or a question? Then if we sketch a graph for a stress and strain, on y-axis we have a stress, and on x-axis we have a strain. So when we sketch a graph, example is, as we know, stress is directly proportional to strain. So there must be a straight line which is passing through the origin. So last point where the stress is directly proportional to strain, we call that as a limit of proportionality. What about the slope of this graph? When we work out the slope of the graph will be stress divided by strain. So stress divided, because quantity on y-axis divided by quantity on x-axis will give us the slope. So stress over strain is the Young's modulus. So if I need the Young's modulus, I can work out the slope. The Young's modulus, what is the like significance of the Young's modulus? The Young's modulus give us an idea about the property of a material. If a material is having a high value of the Young's modulus, it means that material is a stiff material, means it is difficult to deform a material. So if a material is having a lower value of the Young's modulus, means it will be less stiffer or it can easily deform. So the slope of this graph gives us the Young's modulus. And what about the area of this graph? Area of the graph is a quantity on x-axis or y-axis multiplied by quantity on x-axis. So on y-axis we have a stress, on x-axis we have a strain. What is stress? Stress is force acting on unit area. And what is strain? It's a change in length over original length. So force multiplied by, because if I write in terms of units, the unit of the force is Newton, unit of the change in length is meter, unit of the area is meter square, and the unit of a length is meter. When I simplify, it will give me Newton meter divided by meter cube. What is Newton meter? Newton meter is joules. And what about, so what I get when I work out the area of this graph, I will get Newton meter or joules divided by meter cube. Joules is a unit of energy and the meter cube is a unit of volume. So area of this graph will give us energy stored per unit volume, or which is also known as energy density. So energy density, what is the meaning of energy density? Energy density shows how much energy this object will store in a unit volume. So when I work out the area of the stress and strain graph, I'll get the energy density. But when I work out the area of the force and extension graph, I will get the total energy. Because if force is on y-axis and extension is on x-axis, or the change in length on x-axis, and we work out the area of this graph, so area will be force because area will be quantity on y-axis into x-axis. So force into extension, force is Newton and extension is meter. So Newton meter will give us joules. So when I work out the area of this graph, I will get the total energy stored in the object. But when I work out the area of the stress strain graph, I'll not get the total energy. I'll get the energy density or energy stored in a unit volume. And when I work out the slope of this graph, the slope will be quantity on y-axis divided by x-axis. So I'll get the spring constant or the constant of proportionality or the Hooke's law constant. The shapes of the stress and strain graph will be identical as force and extension graph, but the slope for a stress strain graph give us the Young's modulus, where slope of the force extension graph give us the spring constant, where the area under the graph give us the energy density for a stress strain, and the area under the graph for the force extension give us the energy stored. Is it clear? Any question or doubt in this? The relation between stress strain and the Young's modulus? Like this is a word example. So a wire fence is there. Yeah, I will explain the Young's modulus. Look, when we have a graph between the stress and the strain, when we have the stress on the y-axis and we have the strain on the x-axis, according to the relation, the stress is directly proportional to strain. Stress is denoted by epsilon and stress is, sorry, denoted by sigma, and strain is denoted by epsilon. So when two quantities are directly proportional mathematical equation, it must be a straight line which is passing through a region. So when I work out the slope of this graph, the slope is the quantity on y-axis divided by quantity on x-axis. Which quantity on y-axis we have stress on y-axis, and which quantity on x-axis we have strain on x-axis. So stress over strain will give us a Young's modulus. So when I work out the slope of this graph, I will get the Young's modulus. And what is the significance of the Young's modulus? Young's modulus gives us an idea about the stiffness of a material, like whether the object or material is stiff or it is rigid or hard, uh, or it is easy to deform or difficult to deform. We can identify from the Young's modulus. Example, a high carbon steel is having a higher value of the Young's modulus as compared to that of a low carbon steel. So this gives an indication that if I want to use a high carbon steel, I should use in a place where I don't want a deformation. Where in a low carbon steel, which is having a lower value of the Young's modulus, so it can deform easily. So I should use in a place where I want a deformation of an object. So that's why like the car bodies are made up of a low carbon steel, which can deform and absorb greater amount of energy. So if we work out the slope, we get the Young's modulus, the stiffness of a material. But when we work out the area of this graph, area is a quantity on y-axis multiplied by quantity on x-axis. So on y-axis we have stress and on x-axis we have strain. Stress is force over area. Like the unit of the stress is same as Newton per meter square or Pascal, and strain is a change in length divided by original length. So Newton multiplied by meter, it will become Newton meter. And meter square multiplied by meter, it will become meter cube. So Newton meter is joules and the meter cube is a volume. So this is a unit of energy and this is a unit of a volume. So when I work out the area of this graph, what I will get? I will get energy density. What is the meaning of energy density? Energy density means how much energy is stored in a 1 meter cube volume. Like if I have, say, this was a sample was there, this object was there, this object is, say, having a volume of 10 meter cube. But how much energy is stored in a 1 meter cube? How I will know? I will use the area of this graph. So when I use the area of this graph, I will identify that how much energy it will store in 1 meter cube. But if I have a force and extension graph, and when I take the area of this whole graph, what I will get? I will get the energy stored by the total volume. So stress strain graph just give us the energy density, where force extension graph give us the total energy stored by the object. Is it clear, the last explanation? So this is a word example, a wire fence. A wire fence is made up of a steel wire which is having a diameter of 2.5 millimeter. A 1500 Newton force is applied to tension a single length of this wire. Calculate the stress. Stress is force acting on unit area. because this is a wire. So as I mentioned, what is the cross-sectional area of the wire? Area of the cross-section of a wire is pi r square, or you can also use pi d square by 4. Because if I substitute in place of radius, if I produce d by 2, diameter half, so it will become pi d square by 4. Or you can also use a formula that pi, radius is half of a diameter, so d by 2 whole square. So the force which is applied is 1500 Newton. Pi is there and the radius is, the diameter is 2.5 millimeters. So I have to convert into meter. That's why it is divided by 1000, or 2.5 exponent minus 3 divided by 2 and then square. So what we get 3.1 exponent 8 Pascal. The second part, we need the Young's modulus. If the Young's modulus, remember one thing, the Young's modulus are in like gigapascal or megapascal. It's a very high value. So the unit of the like it's the suffix which is used, the prefix I mean, which is used is in giga or tera or megapascal for the Young's modulus of the materials. So the Young's modulus is given. Calculate the tension produced in 33-meter length. So the Young's modulus is equals to stress divided by strain. The Young's modulus is given 210 giga, so it will be 10 power 9. Stress we already calculated in our previous part, which was 3.1 into 10 power 8, and we can work out the strain. So first we work out the strain, cross multiply. So the strain will be equals to 3.1 exponent 8 divided by 210 exponent 9. What is the strain here when we calculate? What is the strain? 3.1 exponent 8 divided by 210 exponent 9. What is the value for the strain? (3.1 exponent 8 divided by 210 exponent 9). (1.47 exponent 3). So we got the strain 1.47 into 10 to the power negative 3. Now we need, okay, 1.47 or 1.48 exponent. Now we need the change in the length. So we know that the strain is the change in length over original length. If I need the change in length, so I'll just multiply the strain with the original length. So strain was 1.7 into 10 to the power minus 3 multiplied by original length was 33. When we multiply them, this will result in the value for 0.048 meter. That will be the strain. Is it clear, this one? Now, if we have a stress and strain graph, or we have a force and extension graph, because the reason why I did not label anything, because this will be same if it is a stress strain graph or it is a force and extension graph. First thing, from O to P, it's a proportionality relation, and because the gradient of this graph, because if it's a stress strain graph, we can define the Young's modulus through the gradient. The gradient of this region will give us the Young's modulus. So I can take any 2 points, and even if I don't take any 2 points, I can take any 1 point, because the first point is already 0. So I can take like the point on y-axis and the point on x-axis, and when I divide them, I will get the Young's modulus. Then what is point E? The point E is actually showing the elastic limit. What is the elastic limit? Means beyond this point, the object will not return back to, like if we cross this point, the object will deform permanently, or it will not return back to the same original length. Then we have another point which is parallel to the strain axis, what we call this region, this whole place, when our graph is almost parallel to the strain axis, we call that as a yield point region. The yield point region, what the yield point region shows, it shows that for a very small change in the length, for a very small change in the force, there's a maximum change in the length. So whenever our graph becomes almost horizontal or parallel to the strain axis, that region of the graph is known as the yield point. And anywhere within in this yield point, I can mark a point. I can call that as a yield point region. So what happened from E1 to Y1, that elastic limit has been reached and the wire yields and it's weakened temporarily. So because there is a attraction, this is about the graph of the wire. So there are attraction, the intermolecular force is there, the metallic bond. So when we are applying too much force, the metallic bond as the layers start to slide over each other. So that momentarily the strength of the metallic bond decreases. So when the strength of the metallic bond decreases, we produce a maximum change in the length. So when we produce a maximum change in length, what we call that as a yield point region. Is it clear till this point? The explanation from P, E, and Y1. Anyone having a doubt till this point? So if I show in terms of the structure, say this was a wire which was having a layer structure. Now, when we apply the force, the extension increases with the same amount till this point. Then it start to deform. When it start to deform, now what happened? One of the layer has been slided over the other. So the length of the wire has increased. Before it was like 3 layers. Now it will have 2 layers. So when the wire is subjected to a force and we stretch drawn them like a metal is there and we draw them into a wire, what we call that as a ductile. So means in this region, what will happen? The material become ductile. This region, the material will become ductile. Then so this whole, and it become easy to stretch. That's why you can see we reduce the force, but it has stretched. Why? Because the layers before it was like, for explanation, before it was 3 layers which were having a stronger force, but now the same number of the particles, but how many layers we have? We have 2 layers. So 2 layers will have a weaker force as compared to the 3 layers. That's why it will become easy to stretch. Then the material again, it is now have 2 layers, and these layers again, they have a force of attraction or a metallic bond. So when we further apply the force, the extension will also increase until we reach a UTS known as the ultimate tensile stress. So UTS for a small strain that cause the largest extension, like we change the force less, but the object deform more, we call that as a UTS or ultimate tensile stress. So UTS is actually the maximum stress which we apply on the object. We call that as a UTS. So in short, UTS is the maximum stress which can be applied. And then we have a fracture point or a breaking point. Means after some time, the force is too much that it crack or break the wire. So we call that as a fracture point. So this is a graph. So we have these graphs, different shapes of graphs are there. This is for a wire, a pure metal. This is when we have a pure metal shows this type of a graph. but we can have alloys as well. Like here, another graph is there. The last point, like this is a linear region where extension and the force are directly proportional, or stress and strain are directly proportional. And the straight line means the Young's modulus we can work out. Then we have an elastic limit. Elastic limit is a point beyond which the object will not return back to the same original length. Then after elastic limit, we have a region which we call a yield point region. Yield point region means for a very small change in a force, maximum change in extension, we call that as a yield point region. And at this point, the material show a large increase in strain for a very small change in stress. Then there is UTS. What is the UTS? UTS is the ultimate tensile stress. We may have a graph going down, or we may have a graph going up. It depends on the material. From material to material, it changes. For a pure metals, when we have a pure metal, it will go down. But for alloys, it will go up. Like this is a comparison. We have a high carbon steel, a mild steel, or a low carbon steel, and a copper. Which material is having a lower value of the Young's modulus? Which material is having a lower value of the Young's modulus? Is it high carbon steel, a mild steel, or a copper? Which is having a lower value of the Young's modulus? The Young's modulus shows a slope. The slope of the graph shows the value of the Young's modulus. So which is having a lower slope, like smaller slope. So copper is having a smaller slope, means copper is having a lower value of the Young's modulus. The high carbon steel, as you can see, why the high carbon steel, it's not ductile or malleable, because say these are representing the iron atom or ions, and it contain an impurity like carbon is also there. So due to the presence, the high carbon steel contain a greater amount of a carbon. So as a result, the layers cannot slide over each other. If the layers cannot slide over each other, it cannot deform. That's why the high carbon steel is having a higher value, like it is much difficult to stretch, or it does not show a deformation, or a very small deformation it shows compared to a low carbon steel or a copper. If you compare the deformation for the copper show a greater deformation as compared to a high carbon steel. Why? Because in case of a copper, which is a pure metal here, there are no impurities, so layers can slide past each other or slip over each other easily as compared to a high carbon steel. So high carbon steel is rigid, where a copper is malleable or a ductile because its layers can slide or slip past over each other.